This is part 2 of optimization with linear programming. We're going to look at 2 application problems. First one, a recycling plant processes used plastic into food and drink containers. So there's 1,200 tons, up to 1,200 tons of plastic, and at least 300 tons must be processed for food containers, at least 450 tons for drink containers. So we need a total of 1,200, and we have to have minimal amounts of those. Okay, and this would be a good place to tell that tons of plastic per week. Food containers, drink containers. The profit is 750 per ton for food and 20 per ton for the drink containers. So with this information, we can find out what the profit is if the plant maximizes production. So let's think about what these are telling us. First, I think it would be perfectly appropriate to use F for the food. Well, now let's see if I can get this to write a little bit better. Maybe I extend it a little bit. F will stand for food containers, and D for the drink containers. I guess CONT for containers will work. Now, we know from the information here, okay, first that together you have to come up to 1,200 pounds. So the amount of food containers processed plus the amount of drink containers processed has to be less than or equal to 1,200. Okay, so we can actually, well, we'll come back to that one moment. We also know that the amount of food containers has to be greater than or equal to 300. At least that many means you can have that many or more. And then the drink containers is greater than or equal to 450. So greater than 300, greater than 450 or equal to. Okay, so what we have now are 3 equations. So let's figure out here what's what. Okay, food and drink ones. So to some extent, it doesn't tell us which is which. In this case, the food containers and drink containers, neither of them is an independent variable or dependent variable based on the other one. So it really doesn't matter which ones. So I will choose to put food containers here. Containers, and drink containers here. Okay. So now the numbers on them, we're going to go up to 1,200 here. So this lends itself really well to 10, 10, 20, 400, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1,200 is not that much further. I think extending this to 1,200 will do me more benefit than trying to play with like 750 at a time, 75 at a time, or something like that. That means on the other side also. So I'll go out to 1,200. We can easily match these up at the appropriate places here as we need to. Okay, so well, I don't have to draw all those lines out. Maybe I'll play with the ruler in a moment. 1, 2, 3, 4. So this will be 500. Okay, and then this will be, because this would be 100, and that'll be 500, and this one would be 1,000. Make sure I counted right. 2, 3, 4, 5, 6, 7, 8, 9, 10, and then of course the 1,200 at this spot. Okay, and then over here will be the same kind of thing. Have to do at least minimal numbers in order to make it sensible to anyone who looks at it. All right. Matching with that one there, matching that there. Pretty obvious where those should be. Now we're going to graph these. So we're going to start with, I'll use blue for that one and green for that one. And might as well, now I'll use black for this one, then we'll use red for the filled-in area. All right, those are my 4 main colors on it there. All right, now let's take a look use the ruler for the first 2 that are easy. So let's find the food at 300. So 300's here. Go to 300, I'll draw a line there, and we know it's going to be greater than that. That's going to be the blue one. Okay. Arrow here and arrow here. And that one is F greater than or equal to 300. Now the green one, 450, that's D, that's like the Y value one. So 450 will be right about here. That seems reasonably close. Let's see how the line draws it. Okay. Green arrow. And I don't want to write over here on it, though. I think I'm going to be okay with it. I actually should go a little further because the actual length of the graph has been extended. Well, didn't mean for that line to go there. Meant to go like this. A little bit more on that. And the blue one I'll try to do by hand. Okay, well, that's not perfect, but not so terribly bad. And the green arrow here. And this particular one then is D greater than or equal to 450. Okay, well, better. Now let's look at the last one here. Put that in black. This one I can do intercepts. If F is 0, we're at 1200 for here. Didn't want it to go away. Now let's see if I can do. Come on, need to put a nice little circle there without that line going away. Got this problem this thing does about. Okay, so there's one. The other intercept would be at this 1200 when, well, let's see, when F is 0, when D is 0, we're at 1200. So I could make this into a y-intercept, and I would usually do that. I'd bring it over and say D is less than or equals 1200 minus F, or negative F plus 1200, and use slope and all that. But this is a place where intercepts makes it much easier to just very simply put 2 points and draw a line between the 2 points. Okay, that seems to match the 2 points up okay. Don't need a ruler anymore. I need to do an arrow. Now let's get that line back. Have an arrow on the ends. Okay. And then this one is F plus D less than or equal to 1200. Well, there's places where they meet. Let's go real zeros here. Well, now we can see that's a less than, so it's all this area. The green line, it's greater than. The blue line, it's greater than. There's our area. So at this point, it's now become actually, as soon as you made the equations, this becomes like the 4 problems in part 1 of the lesson. Fill in enough of this to say I happily had fun with the red pen or the red part of it. Okay. Good enough. Oops, now it goes away. I should have left it, should have left well enough alone here. All right. We have a vertex. And we have another vertex, and we have another vertex. So let's take a look at where those vertices are. And that's where we're going to come down here, okay, to write them out the way they should be. So this one here looks like it's 300 and 900. 300 and 900. Okay, and down here, this one looks like 300 and 450. And over here, okay, well, the y value is 450, and it looks like it's in between the 7 and the 800. So it's 750 and 450. And we'll come down here and put those in. So we have 300 and 900. And we have a 300 and 450. And a 750 and a 450. So we have 3 vertices, 3 to check out. We need the equation to go here. And that's given to us through the profit part. So 750 per ton for each F and 20 for each D. So that one looks like it should be, I guess I'll do it with those. Go right for me. It's not writing. Let's see if it'll cooperate a little bit more when I redo it. 1750 F plus, the other number was 20 plus 20D. Now, thing is, we don't have to have it equal to or less than or anything like that. It's just that we have those two parts of it to make the expression that we need to fill these in with. So it's going to be, let's go back to Blackboard, 1750F plus 20D. Much easier if they give it to you. Some problems don't, and I'm actually going to talk about that for one that's in the work, textbook work. But thankfully you'll get these, and so I will be semi-reasonable on my test and maybe give them to you there. Okay, so now let's calculate that. So if we do 300, well, I guess I should do it with 1750 first on that. So it'd be 1750 times 300 plus 20 times 900. When you work that out, the total is 23,795. It's 23,250. So we're at that much for that one. On the next one, 1750 and 300 plus 20 times 450, 1750 times 750 plus 20 times 450. I apologize for some of these numbers being messy. It's just this pen is really much harder to write with than you'd think. It works perfectly at other times, and sometimes I'm just not able to get it quite right. But you can see where I'm going with the numbers, and see, especially I'm going really slowly and carefully getting the final ones on here. When you calculate these out, these are the results. So this one tells us, since the question specifically is a maximum, nothing about the minimum, what's the profit if the plant maximizes production? And this says that the profit is this amount. So they must actually charge more than that to get some of their expenses back before they have profit. So I'm going to guess this is a 25F plus 30D or something like that, or I don't know, whatever it might be. But what this does show us is that clearly one of them is larger than the others. And because that's the maximum, and it says, what is the profit if the plant maximizes production? Okay. The maximum profit, that's a good summary way of saying it. Maximum profit would be 23,250. Now I can say that if this was a test question, you answered with just the 23,250, that would be acceptable as long as you include the dollar sign. That's an important unit. If you don't include that, then somebody, without really understanding the problem, and you need to treat it as if I don't know what the answer is supposed to be, would think it could be 23,250 widgets or 23,250 people in a stadium or something like that. You wouldn't know it's dollars unless you specifically say so. So make sure you say so. You always include units when it's appropriate. So this problem, like many others, many word problems, once you take the word problems and you make it into the type of equations that make sense, then the rest of it is just the same thing that you've done already. We're going to do the same thing now in the second example. Veterinarian's office schedules 20 minutes for routine office visits, 40 minutes for surgeries. The veterinarian cannot do more than 6 surgeries per day, and 7 hours available for appointments. Now then, this part about the costs will come later, because we'll then use that with the vertices to find a combination that maximizes the income. So let's look at our restrictions here. Right, so first, we know we're going to have some, the X and Y's are all past 0. So in a way, you know, that's an easy one. I thought about putting greater than 0 and less than 0. I'm not sure how much or if I should write that out on them too. What we have are, well, we know cannot do more than 6 surgeries per day. So let's start with that. Okay, well, first, office visits and surgeries. Let's call these X and these Y. Now you could do like O or R and then S. I'm going to keep it to X and Y. So I'm going to say X, office visits, understood that it's routine, and Y are surgeries. Okay. So on this, we now know that the Y's have to be less than or equal to 6. All right. So we can graph that at 1, 2, 3, 4, 5. Actually, let's make the other equation first. Okay. Now here's one thing. We're dealing with minutes and then hours. We could change the 20 minutes to 1/3 of an hour and 40 to 2/3 of an hour, but it's probably more reasonable to instead say that you have 7 hours equals 420 minutes and use the minutes for totals. Minutes. Okay, sooner or later get that in. All right. The reason we'll do that is because we know that each office visit is 20 minutes and each surgery is 40 minutes. So we can now say that the number of office visits times 20 minutes plus the number of surgeries times the 40 minutes has to be less than or equal to the 7 hours in the day. I was tempted to say that we would also say that the number of office visits has to be greater than or equal to 0, and the number of surgeries has to be greater than or equal to 0, but that's almost understood when you see on the graph that you're starting off with zeros anyway. So we know we're not going to be in these areas at all. But now is an appropriate time to write what they are. So since I said X was office ones, let's go ahead and write office visits here. I think I don't like having those little marks now on those. So this is one where I think it's understood. You're not going to negative surgery or negative office visits on it. So I don't need to graph those necessarily. Office visits. If it wasn't a real life problem, then we would have to do that because negatives could exist in something. So you would have to if we had the 4 quadrants and it wasn't an application problem. Okay, and then here we have surgeries. Supposed to be an R there. Okay, let's rewrite it. Surgeries. Okay, and then now numbers we go up to, let's think about it before we put the numbers. Because it looks like, let's take the 20 minutes. That's 3 in an hour. In 7 hours, that would be 21. So you can go as high as 21 of them. So if you can go as high as 21 of them on the office visits, then I would do these as 20s and make a 21 here just in case. So that's 20, 21. That means 2, 4, 6, 8, 10 here. Okay, and then I'll do the same thing on the other one. But with surgeries, we can't go that high. If there's no more than 6 surgeries a day, we're not going to go that high, but I'm still going to keep it with 20s here. Okay, 20, 2, 4, 6, 8, 10. Now we know that this would be the maximum of surgeries possible, and let's now actually graph that. So we're going to graph this one, and we're going to graph this one. All right, so let's make this one a blue one, and this one a green one. So on the blue one, easy to graph because I just need to come here and do this out a little bit more to cover that last part. Putting a couple of these and saying, oops, then I actually need to put that out here. Let's say that that's Y greater than or equal to 6. Now on the other one, okay, now I could put zeros, but then we're talking, these are number of visits. Now let's think about that. It's the number of visits, but it's still an equation with this. We need to divide and graph and see what's, for this one, I need to change this one around. So I need to subtract the 20x. I get 40 y less than or equal to negative 20x plus the 420. Okay, and now what I'm going to do is divide everything by 40. So I have y less than or equal to negative 1/2 x plus 10.5. Now that one will fit on this graph. 10.5 is going to be just about here because 11's in the middle. And then negative 1/2. Well, if you keep going negative 1/2 here, I'm going to do the easy one. When y is 0, bring the 10.5 over, multiply by 2, it's 21. So I'll find the intercept for that. So basically, I did this one with the intercepts. Like in some other problems, sometimes that is actually easier to work with. This one in there, almost there. Okay, close enough for a hand graph. Now let's think about what this tells us on replacement. So we are less than 6 for the blue one, all down here. No, I'm going to do the red. So we're all down here. It could be down here too, but however, the green one is a less than also, which means it's also down with all of these, but not this area, and they can't use this area. Here we are. Okay. Now this, I can actually make this a larger thing to write with, but that's actually more time to go do that than to just do this. Sometimes it doesn't return right to the size that I want afterwards. So I think we'll get the idea here. Take just another 5 seconds or so. So we're in this area. That also helps to identify very clearly the vertices. We have a vertex here, and a vertex here, and a vertex here, and a vertex here. So, and I want to go over it. So this one is at 21 and 0. This one is at 0 and 6. Parentheses. Actually, I think I'll write it over here to 0 and 6. 0, 0, I'm not sure that's going to do me much good when I figure it out. I'll put it in anyway because there happen to be 4 spots and there's 4 vertices. And this one here looks like it's halfway to here and it's not, and it's 6, so that's 9 and 6. Okay. So 0, 0, don't have to really when you think about it. 0, 6, because it's definitely going to have a result, definitely should be in it. 20. I'll do the 9 and 6, and then I'll do the 21 at 0. Now let's get the equation that we need, the expression that needs to go up here. I'm going to make these better parentheses first. Okay. So coming back up here now, let's look at office visit costs 55 and a surgery costs 125. So that means we can say 55 x plus 125y, and that's what we'll put in here. So we simply get that from the costs that they say here. Now, is this profit or total income? No, that's just the amount of money to come in. They'll maximize the income. The income is then use some of it to cover costs, some of it would be profit. All right, so we just want to know what the total income is going to be. 0, clearly that's 0, goes away. So here we have 55 times 0 is 0, 125 times 6, which is 750. 0 plus 125, come on, and 6. So here we have 55 times 9 plus 125 times 6, which calculates out to 1,245. Okay. And then the next one, 55 times 21. Now that's going to be a lot. I don't even need to put plus 0. That one's going to be that. That's going to be a lot, but it's not enough to make that the maximum. So this says then that the maximum income would be if it's 1,245. So actually then let's see. So it says, find the combination that will maximize the income. So this is not the answer. This is the answer. So the best combination, the best income combination would, let's write that one better there, would be 9 office visits and 6 surgeries. 9 office visits and 6 surgeries. So if this were a question on a test, make sure you say 9 office visits and 6 surgeries. Don't say 9 and 6, because you're not clarifying which is which. No matter what order it is, you're not clarifying it. You have to specifically say that. And don't say like 9x and 6y, because the problem didn't tell you x and y or a and b. It said office visits and surgeries. So you have to revert back to what it really was. But this does show how if you take the information here, you can get the lines that you need to graph, get the vertices from that, and then use the cost information to maximize the, in this case, the income. Okay, now I want to bring up a question from the textbook, which involved, actually pull that one up, that involved something that wasn't covered clearly in instruction in the textbook. Okay, so let me find the particular thing. Okay, so this was from section 3.3, and it's question number, I believe, 25. Okay. And this is the one that says that Sean has 20 days. 20 days to paint 45 structures. Some of them are sheds, and you can do 2.5 per day. Some of them are playhouses, and you can do 2 of those per day. Okay, so that's pretty much the information that's given. A combination of these has to be less than or equal to 45, and you can do only 2 a day of houses and only 2.5 a day of sheds. Right, so there are a number of equations you can make with. Some of them are pretty easy. So let's say we call this one A and this one B. Okay, so A is going to be greater than or equal to 0. B is going to be greater than or equal to 0. Right, and you could do all of one or all of the other. Together, A plus B is going to be less than 45. The other equation takes a lot more thinking. You think about this as the number of possible A, the number of possible B, or sheds or houses. This one is the total number of houses, or how many you can make of them, total number of things, or total number of structures. The other one needs to be based on how much per day, per the 20 days, or because it needs to be based on the days, not on the structure. So a way to think about this is think, how long does it do just one A? Well, if you can do 2.5 by day, that means that let's rephrase it. How long does it take to do just one of the A? One shed. Well, if it takes 2.5 that you can do in a day, that means to do one of them takes 40% of the day, or 2/5 of the day. So 2/5 A, you can do 1 and 2/5 of a day. You can do a half of a house in a day, or this guy Sean can actually. So Sean can do 2/5. Each time he does one, it takes 2/5 of the day. Each time he does a house, it takes 1/2 of the day. the number of A's that he does plus the number of B's that he does would be multiplied to this. However many A's times 2/5 would be that many that he does. How many of these times 1/2 would be that many that he does. Okay, and then that, here's the thing on it, has to be less than or equal the 20 days. So so this will give you how many days. If he were to do, let's see, so if the number of this was 40, 40 times 1/2 would be 20, this would be 0. If this were 0, in other words, say if none of these were done, then you multiply by the 2, and then the B has to be less than or equal to 40. So it would be 40 houses that he could make in 20 days. Multiply this one, same thing. If there were no houses done, it was sheds, okay, we multiply with 5 over 2 would be 50. So the maximum number of sheds that could be done would be 50, which is true if you think about it another way. Now, let's multiply by the LCD. Both sides. Cancels out here, we get 4A. Cancels out here with a 5 plus 5B. 10 times 20 is 200. This is the one that if people looked at the solutions, people saw that quite a few people were like, how'd they get 200? So some of people realized this, that it was based upon the days here. I think the solution should have said that, but now I've shown you the key to that. With this information, you can now go ahead and finish the rest of it, because the rest of it is just following the same way that we did everything else. But this is the thing that for some people, it will help a lot more to see this. If you already did do this problem, you don't have to continue going back to it. You get the lesson on in here. Don't worry about it. If you already submitted it, I will not discount it for anyone. So what we have here as a reminder is how to do application problems, which is primarily figure out from the wording what kinds of inequalities you should make, and then you're home free, just like the ones that didn't work word problems. And it just becomes a non-word problem once you make these things. Okay, same thing here. You work on, you use the word problem just to make equations, or inequalities in this case. And once you have your inequalities, you're ready to graph it and figure out the vertices and figure out the maximum and answer the question based upon what it's being asked. In one case here, you asked for the amount of money. Another case here, you asked for the combination that would lead to the highest income. And then here now you have the key of why we got that part or that type of equation or inequality rather, and it wasn't explained clear enough. Now hopefully this makes sense. Okay, thank you for listening and watching, and hopefully this was helpful.